Hello and welcome to my talk investigating parallelization of MAML. My name is Jan Bollenbacher. My co-authors were Florian Soulier, Beate Rhein and Laurenz Wiskott. This work is done by a cooperation between TH Köln and Ruhr-University Bochum. When we think about learning in machine learning, we can divide the learning into three stages. The first stage is transfer learning. So we train one artificial network on a dataset, so for example ImageNet, and for classes 1 to class 1000. Then we transfer the previously learned network and train it on a different dataset. In this example, the my-dawn dataset, and for classes 1 to classes 45. And the assumption is that the weights learned previously before transfer learning or before transferring the weights will help us to classify the classes in the new dataset. Therefore, we will need to retrain at least the last layer where the mapping between high-level features and classes is done. In stage 2 of learning, for example, one reinforcement learning agent learns in training time the tasks walking, hiking and biking, while in test time the agent performs well on the same tasks but on a different terrain. And the third stage of learning is meta-learning. So the agent learns in train time to hike, stand, run, and in test time the agent learns a new task very quick, for example ice skiing. In this work we want to focus on stage 3 of learning, meta-learning. In meta-learning there are three classic benchmark tasks. The first one is a regression task, the second one is a classification task, and the third one is a reinforcement learning task, but this is not done in this paper. And this is the benchmark task regression. Every sine wave is a new task. The learner gets a certain number of points and needs to adapt very fast. In this example, the learner gets 10 points for training and needs to learn to interpolate new points. The output of different learners is showed using the dashed lines. In the classification task, a learner gets for meta-training, as shown, one instance of 5 different classes. The classes are labeled from 1 to 5. The learner now needs to adapt its weight so that it classifies the instances of the test set correctly. The learner cannot learn to remember the IDs of the class, but needs to find a good set of weights to adapt so that it classifies the classes correctly. In meta-testing time, the learner performs on classes never seen before. This setup leads to the possibility of learning to classify classes using a dataset with a very small number or no instances of the classes for training. For validating our algorithm, we used the mini-ImageNet and the OmniCloud dataset. In mini-ImageNet, we are facing 64 classes for training and 36 for testing. Using the OmniCloud dataset, the training set consists of 3,760 classes and the test set consists of 2,732 classes with 20 instances each. The results shown in this presentation are obtained using the OmniCloud dataset. MAML does not learn an update function or learning rule, it learns the model parameters in a fully differentiable way. The parameters learned are suited to adapt very quickly to new tasks. Imagine model parameters theta in weight space. We want to optimize the parameters for three different tasks. For each task, there exists an optimal set of model parameters. We now calculate the gradient of the loss for each task. We optimize on all three different losses at the same time to receive parameters theta prime. Theta prime is a good compromise between tasks. Starting from theta prime, the optimal parameters can be found by using just one or a few gradient updates. In this work, we investigate the parallelization of MAML. We see the need to investigate this because MAML is computationally very expensive. It is also interesting to know which parameters and parallelization strategy leads to a better and faster learning. Also, with our architecture, MAML can be rolled out to a whole cluster of servers. We propose distributed MAML as a form of parallelization. There is a central learner holding a meta-model. This model is copied to a number of workers, in that case 2. Each worker applies a number of MAML steps to the model, in our example also 2. Each worker therefore uses individual tasks drawn from the training set. After the last MAML step, the model is sent back to the central learner and the weights are merged. In our experiments, we want to solve the question, which impact does parallelization have on learning? Also, we want to clarify which impact the number of parallel workers and consecutive MAML steps have. The last question addresses the scenario if we have the possibility to parallelize sampling tasks or if we need to sample in series. In this experiment, we ran DMAML using 1 MAML step per iteration and 32 tasks in the inner learning loop. We can show that this accelerates learning and converges to a higher accuracy. This comparison only holds if we have a lot of resources and tasks are cheap to sample, because in one step the learner with 32 workers gets 32 times more tasks to learn. In this experiment we set the number of tasks per step to 32 and the number of workers to 4. We only vary the consecutive MAML steps per run. As one can see, there is no benefit in applying more steps. We assume that the rough direction of the parameter update is important, rather than the exact numbers. In this experiment, we keep the ratio of tasks sampled and workers equal. We can see that a higher number of tasks per MAML step leads to a better result. We assume that we update to better parameters if we see more and various tasks per step. We also compared the case of perfect parallelization and perfect serialization. If we are able to sample tasks parallel, it is best to use as many tasks in a MAML step as possible. On the other hand, if it is costly to sample tasks, it is better to aim at less tasks and apply more MAML steps. To conclude, we have shown that if computing power is not the issue, parallel workers accelerate learning. In the case of perfect parallelization, we need to use as many tasks as possible in one MAML step. On the other hand, in the case of perfect serialization, we aim for many MAML steps with fewer tasks per step. So, if it's possible, try to parallelize the inner learning loop. So, thank you very much for your attention. I'm very happy to answer your questions. Please stay safe and healthy. Goodbye.